This conference will now be recorded.
Thank you, Kishore. Thank you for joining me this morning. So, last Friday, this is what we were discussing. We have stopped at this point, and as you know, we are discussing about training the models and what are the important aspects that undergoes when you're training a model. Okay, so we paused at this point, and we are talking about RMSE and MSE. So, if you see at the diagrams, the RMSE and root mean square error and mean absolute error are the ways to measure the distances. Distances is again nothing but the distance between actual values and the predicted values, and it is also called as distance between two vectors. Again, I explained you a vector means nothing but a predicted vector and a target value vector. Okay, and vectors is represented with the small bold letters, and matrix are represented with capital bold letters. You must be aware of it. If you tend to confuse between these things, then please be very careful. You have to understand vector is very important. It's nothing but a collection of arrays, or it can be, for example, called as a future vector. Simple. Now, there are various distances, measures, or norms to calculate the distance between two vectors. First one is Manhattan vector and Euclidean norm. Now, red, yellow, and blue paths, as shown in the diagram, will travel along the orthogonal city blocks, which is called Manhattan distance. Now, look at the diagram carefully. You have red, which went left side to the end. You see yellow, which went to right side to the end. If you see green, it diagonally went up, and if you see blue, it had a staircase kind of thing. Now, in here, apart from the green one, red, yellow, and blue paths are Manhattan distance, and green path is called as Euclidean distance. That's the easy way to understand the process. Now, oh sorry, I didn't share the screen. I'm really sorry. Okay, perfect. Sorry, thanks Kishore. Thanks for reminding me. I'm not feeling well actually. I had a very problematic sleep yesterday and last night. Okay, let's get back to the business now. Both root mean square error and mean absolute error are ways to measure the distance. Perfect. Now, what is the distance? Distance is nothing but, again, I'll tell you the fact. Let me draw a diagram. Again, this diagram should be registered in your, if it goes like this, then this is actual value and this is a predicted value. Okay, this is actual value, this is a predicted value. That's an example only. Okay, now remember this diagram, frame this diagram properly so you'll not confuse yourself. In here, what is happening is there are various distances, measures, or norms. Now, various distances, measures, or norms is nothing but we have Manhattan norm and Euclidean norm. Okay, in this process, red, yellow, and blue paths, apart from green one, will only travel along orthogonal city blocks, which is called Manhattan distance, and green path is called Euclidean distance. This is all you need to understand. You need not have to break your head. If someone asks you about Euclidean distance and Manhattan distance, tell them, boss, if you consider a curve or if you consider orthogonal blocks, your yellow, blue, and red are having the orthogonal distance Manhattan form, and the green path is having the Euclidean form. As simple as it is. Okay, nothing to worry in this slide. Now let's go to 75th slide. Now L1 norm. Look at the diagram, guys. Do not get confused with the diagram. Now, if you see the diagram, your V0 and V1 is having a pipe on the left side and a pipe on left side, pipe on left side and pipe on right side. Now, L1 norm is used for the sum of absolute mean absolute errors corresponding to L1 form, denoted as pipe double pipe dot 1. This is also called as Manhattan form. If you take care of L2 form, the computing the root of squares of root mean square error corresponds to L2 norm. Simple. L2 is for root mean square error. L1 is for mean absolute error. Again, Manhattan form is nothing but yellow, green, red orthogonal blocks, and Euclidean distance is nothing but the blue one. Okay, this is what I explained you here. Sorry, green one is Euclidean, red, yellow, and blue are Manhattan. Okay, L1 form is used for mean absolute errors, and L2 is used for root mean square errors. Okay, LK norm. The LK norm of a vector V containing n elements is defined as a formula here. Okay, now here, if you observe carefully, L0 or L of 0 gives the cardinality of the vector. Cardinality of the vector is again number of vectors it has. Now, if you see L infinity gives the maximum absolute value in the vector. You need not have to remember the formula. All you have to remember is, are you aware of L1 form, L2 form? L1 form is used for mean absolute errors. L2 form is used for root mean absolute errors. And LK norm is used for a formula wherein formula has L0 which has cardinality of the vector and L infinity which gives the absolute value in the vector. That's all I can say. Okay, perfect. Now go to 76. Now the LK norm will have the highest norm of the index. When I say highest norm of the index, the more it focuses on the large values and neglects the small values. When I say large values, large error values. When I say large error values, the largest distance between the actual value and predicted value. It ignores the smallest distance because smallest distance mean is a minimal error message. Now, this is why the RMSE is more sensitive to outliers than the mean absolute errors. Again, more sensitive to outliers mean outliers are not overfitting or underfitting. Outliers are the noisy part of your data that is not letting the prediction to be perfect. You need to be aware of this. Okay, next one. But when the outliers are exponentially rare, again, exponentially rare means like a bell-shaped curve. Bell-shaped curve, I explained you already. Whenever you're talking about error message, you should register a diagram within your memory. This diagram, it will be like this, and it may go like this, or it may also go like this, because you'll have the dot values like this, like this, like this, like this, like this, like this. You'll have dot values. Now, when you have But when the outliers are exponentially rare, like bell-shaped curve, the RMSE performs very well and is generally preferred. Okay, guys, this training model is all about theory because we have done enough practicals and we dealt about RMSE, MSE, and a lot of other things. But now we need to understand underhood concepts, and that's the reason why we are doing it. Okay, so here what happens is the outliers are exponentially rare and RMSE performs very well and is generally preferred. Now, L1 versus L2 regularization. Again, guys, we talked about normalization. We are talking about regularization. Normalization and regularization are nothing but they are kind of the methods that you use to control the errors or to control the curve shape where it has errors included in it. Now, L1 can yield sparse models while L2 doesn't. Now, you may ask a question, what is sparse model? I think I explained the slide already. It's coming to my conscience, but that's fine because this is very important. We need to know about it. Sparse models are nothing but the models that are actually not accurate, but having to learn an estimation from it. Okay, So you need to understand this one also, guys. This is very, very important. L1 versus L2. L1 is for MAE, L2 is for RMSE, and you know LK norm. You also understood why RMSE is very good than MSE because RMSE is more sensitive than MAE, and the outliers of exponential ignored. Now, sparse models are nothing but it has the same kind of properties in the machine learning algorithms. Now, when an algorithm, for example, I'll say you, if if your linear regression is giving you a sparse result among all the coefficients, then if most of the numbers are non-zero, then you're fine. If you have any of the non-zero, then that is not sparse model. Sparse model is like the estimation of the near accurate values. Okay. Now, the sparse model is helping in future selection. Again, guys, if you remember, if you will be given 20 columns, in the 20 columns, you must actually use the best columns that are important features for your prediction. For that to happen, you need to know the best important features. That best important features will be found in L1, L2 regularization or L1 is eating the sparse models. Now, it will also tell you which features are important and which features are not important. Ideally, if you understand which features are really important, then you are totally in a good shape and you are saving a lot of time for yourself. That is the importance of it. Okay, let me go back to the pointer now. Erase all the drawings. Go back to the pointer. Now, let's understand the ridge, lasso, and elastic now. So we are the last stage. If you understand this one, this will be completed. We should have completed this on Saturday itself, but Saturday we had a workshop, Sunday we had a workshop, yesterday was not well. So I'll try to complete it by tomorrow, and next we'll jump into support vector machines, and then we'll wrap up this batch. Okay. However, you all are most welcome to be part of this continuous journey. As I told you, the first batch is always always an kind of fail fast method where we don't exactly get the estimates required to prepare the slides, pass the content, give the training, arrange the workshops, take the feedback, and then move on. But this first batch is the best litmus test for me also to understand the amount of efforts I need to put. So second batch will be much faster. I'm sure the more new concepts will be adding with respect to AI, and we will also add so many other aspects of it. Feel free to join. I'll add you all in the groups and I'll keep you posted. So that's the reason I always say my my trainings are not trainings, they are journey. That's the reason I put data science journey with ANR. Data science journey with ANR means, data science is not just 1 month or 2 month course. It keeps on adding, and you need to keep your foot on top of it and update your skills. Okay. Now, let's understand the ridge, lasso, and elastic regressions now. The regularization term in ridge regression is nothing but a ridge regularization. A ridge regression is a regularized version of linear regression. A regularization term is called a cost function. So we talked about normalization, we are talking about regularization. A cost function is nothing but the the parameter or the factor that can reduce the error. Okay, that's very important. Ridge regression is a regularized version of linear regression. A regularization term is added to the cost function. Adding a regularization term to cost function forces the learning algorithm to not only fit the data but also keep the model weights as small as possible. This is the best benefit you get. Okay, now note that the regularization term should only be added to the cost function during the training only. Very important step. Once the model is trained, we evaluate the model performance using the unregularized performance measure. Do not fall into trap. If you're talking about regularization in the interviews, you are you will do the regularization process only during the training process. Once the model is trained and evaluated, the model performance using the non-regularized measure should be done. Okay. Before the model is before the model is trained, you can use the cost function. But once the model is trained, we evaluate the model's performance using the unregularized performance measure. Simple. Now let's revise this one. Reg regression is all about the regularized version of linear regression. When I say regularized version of linear regression, what is the regularization term in this? The regularization term is added to the cost function, and the cost function will help you enforce the learning algorithm to not only fit the data but also keep the model's weight as small as possible. Perfect. It also keeps the model's weight. It not only forces the algorithm to not only fit the data, fitting the data is different, and keeping the model weights as small as possible is also different. When the weights are small, the errors will be small. When errors are small, you will have best prediction. That is the beauty of the rigid regression. So regularization must only be used when you are at training phase. Once your data is already trained and you are evaluating, you should evaluate using the non-regularization performance measure. That's all I want to highlight here. Perfect. Go to 79 slide now. Now, why do we add the regularization term only during training, not while evaluating the model performance during testing? What is the importance of it? Why is it so important that you do regularization only in the training part, not on the evaluation part? Now, cost functions should have optimization friendly weights during training. Very nice. Very nice. That's good. The cost functions should always have user-friendly or optimization-friendly weights during the training, while the performance measures used for testing should be close as possible for the final objective. Okay. Now we may ask a question, Amar, what is the difference between weights and what is the difference between the final objectives? Very simple. The cost functions should have optimization-friendly weights during training, while the performance measure used for testing should be as close as possible to the final objective. Now, when your weights are optimization friendly, you need not have to worry about the final objective. But here, the final objective must be as close as possible. This is the reason why we evaluate the model's performance using the unregularized performance measures. Guys, a simple logic. You divide the data into training set and test set. Training set is used to train the model. But within the training set, you separate few records for the evaluation process. While you are dealing with training set, use the regularization thing, because in regularization thing, you have the optimization function that finds the weights during friendly weights during the training. Whereas if you are talking about evaluation, then you need to use about unregularized performance measures. Okay, now let's talk about ridge regression cost function. Guys, and a quick note for everyone. While I'm preparing the slides, this one is not question mark. This one is actually this one. Please be aware of it. This symbol I couldn't really type properly. That's the reason I had to adjust with this one and wanted to highlight this. Now, ridge regression and cost function. The hyperparameter is the one that controls how much you need to regularize the model. For example, if the hyperparameter equal to 0, then ridge regression is just the linear regression. What did I tell you here? 1 minute, guys. Let me go back to the pointer. Let me erase all the drawings. Now, if you see here, I told you the ridge regression is the regularized version of linear regression. Okay, you got this point. Now, if the parameter is equal to 0, which parameter is that? The learning parameter. If the hyperparameter is equal to 0, then ridge regression is nothing but the linear regression. Now, note that the bias term theta of 0 is not regularized as the sum starts at I equal to 1, not 0. Don't worry about it. In here, what he is trying to tell you is he is trying to explain you the formula implementation under the hood. We are actually not bothered about it, but we need to just understand how the formula works. Now, note that the bias term theta is equal to theta of 0 is not regularized. Okay. Now, theta of 0 is nothing but, one minute guys. Here, theta, you got theta, right? Like this, theta 1, theta 0, theta 1, theta 2, like that, you'll get a set of values. In that values, what he's saying is theta of 0 is not regularized. That is fine. We are not concerned about it. Now, we are just constraining the weights of the features. Hence, regularization of the bias term is not required. Now, do you really need regularization or do you not need regularization? There are two ways of dealing with it. The first thing is, if you are putting a strong control on your weights, you don't need regularization. If you're not able to put the weights constraint on your weights, then you need regularization. These guys in ridge regression, what they're doing is they're constraining the weights. So in that cases, you don't need the cost function or the regularization. Now, if W is the vector of the future weights theta 1 to theta n, now look at the formula. This formula, I'm talking about this one. If W is the vector of future weights theta 1 to theta n, then regularization term is equal to the formula shown, where the pipe and the dot inside the pipe represents the L2 norm of the weight vector. So if someone asks you about ridge regression, tell them, boss, ridge regression has a formula. If the hyperparameter is equal to 0, ridge regression is nothing but the linear regression. Again, ridge regression is represented by a pipe and a dot in it. And ridge regression has a pipe W2 square, which means this is the L2 norm. Again, L2 norm is a form of root mean square error. And if you want to talk a bit high, you can say you can have an option of constraining the weights. So when you constrain the weights, regularization is not needed in the ledger regression. That's all you can say. Hope it's making sense to you. It's all theory. I'm trying to put my best so you understand things carefully. Okay, cool. Now let's get to the next one. Now, what is the important point here? In all this while when you're talking about ridge regression, the regularization, normalization, cost function, learning curve, what understand? Scale the data. When you wanted to scale the data, use the standard scalar before performing the ridge regression, as ridge regression is sensitive to scale of input features. This is very important, very important point. When you are talking about ridge regression, lasso regression, or elastic net, each regression is a bit different. Each regression nothing but the regularization terms of the models. So in ridge regression, as it is very much prone or sensitive to the scale of input features, scale the data as much possible. Okay. Now go to 82. Now, how do you train the ridge regression? Okay. You talked about theory part. Now you also need the practical part. Okay. Now let's train the models using ridge regression on some linear data using different values. Okay. Polynomial regression with ridge regularization. Data is first expanded using polynomial features. Degree equal to 10. Look at the diagram on the left side. My blue line is alpha equal to 0. My green dotted line is alpha equal to 1e minus 0.5. That's something I don't mind. My red is alpha equal to 1. Okay. First thing, what happens if the degree is equal to 10? In the degree equal to 10, we have to use the standard scalar as I told you earlier, because look at the way how the blue line is behaving. It is going too bumpy, right? When compared to red one and green one, blue line is too bumpy, which means it is affected with the outliers. If not outliers, at least it is getting affected with the input features. So use the standard scalar. Now, finally, The ridge models are applied to resulting features. Yes, that's fine. Now, the polynomial regression with ridge regularization is increasing or leading to flatter, which is less extreme, more reasonable predictions. This reduces the model's variance but increases the bias. Again, here go back, we talked about bias versus variance and we talked about bias versus variance trade-off. If you don't remember that, kindly recap. Bias is all about underfitting the model. Variance is all about overfitting the model. Bias is all about your model generalizes too much, and variance is all about your model is too complex and constrained that it overfits. Now, you don't want bias and you don't want variance. You deal with bias and variance trade-off, a middle point between bias and variance, such that you will maintain the balance between it. Okay. So here, if you when you train the ridge regression, the polynomial regression with ridge regularization is reducing the model's variance but increasing the bias. Okay, that's perfect. Now, implementing the ridge regression. Guys, look at the diagram. First, look at the diagram. You have I1 equal to 1. You have I2 equal to 2 by 2 matrix. You have I3 equal to 3 by 3 matrix. Like that. If you go to n, you have I n by n matrix. Now, identity matrices with one of the main diagonal and zeros elsewhere. Okay. In this thing, one thing I want you to observe carefully is 1, zeros everywhere. 1, zeros everywhere. 1, zeros everywhere. Okay. Now, this is called as identity matrices with one of the main diagonal and zeros everywhere. Okay. What is the need of this one? Why are we talking about this piece now? The reason why we are talking about this one is, like linear regression, we can perform the ridge regression by computing the closed form equation or by performing the gradient descent. Now, with implementing the ridge regression closed form solution, we have the formula as shown on the right side, where A is nothing but n by n identity matrix, except with A0 in the top left cell, the bias term, rest all will be ones. That is the important thing you need to understand in the implementing ridge regression. Okay, very simple, straightforward. You have a formula, and the formula I already told you, the bold letters and capital are the matrix. And here, except with A0 in the top left cell, which is a bias term. The top left cell is nothing but the diagonal matrix of 1, 1, 1 numbers. That will be the bias term. That's what he's trying to tell you. Okay, perfect. Let me erase all the drawings. Let me open the pointer. Now, ridge regression with scikit-learn, a closed form solution. Very simple. Go to your scikit-learn dot linear underscore model. Again, as you are using linear regression, your ridge will fall under linear underscore model. So from sklearn dot linear underscore model, import ridge. Perfect. Ridge regression will have parameters. One is alpha 1, solver, and random state. You know why we use random state? With association to that, use alpha and solver. Now, ridge underscore reg dot fit x comma y. You are going to fit your data on your x on your features and labels. Ridge underscore red dot predict. You are predicting at the closed form of 1.5. It has given you some value. Okay, perfect. Now, again, here I'm using the ridge regression with scikit-learn use quadratic gradient descent. Here I have not used quadratic gradient descent. Here I am using quadratic gradient descent. Again, when I am using quadratic gradient descent, I have to use SGD regressor, and I'm using penalty equal to L2. L2 is again normalization. When I do normalization, it is about L2 is RMSC. Okay, random is equal to 42. Now I'm fitting it on my features and labels. The penalty hyperparameter sets the type of regularization term to use. Specifying L2 means we want SGD to add regularization term to cost function equal to half the square of L2 norm of the weight vector, which is fine. Okay, this is how you implement the ridge regression with scikit-learn and the scototic gradient descent. Okay, now lasso regression, LASSO, least absolute shrinkage and selection operation regression. Okay, I repeat, least absolute shrinkage and selection operator regression. Least absolute shrinkage and selection operator regression. Now, as we have discussed about ridge regression, like ridge regression, the regularization term is added to the cost function in Lasso also, but it uses the L1 form of the weight vector instead of half the square of L2 form. L1 form is your kind of MAE, L2 form is again RMSE, but here as your ridge regression is using L2 form, your lasso regression is using L1 form. Again, it uses L1 form of the weight vector instead of half the square of L2 form. Okay, if you look at the example, this is the example of the lasso regression cost function. Do you have any questions? So if you look at our agenda, we have completed this one. Lasso regression is completed. Elastic net, we need to finish it off. And then one important point, logistic regression. If I complete that, we'll finish this slide. I'll complete that in next session. I'll try to prepare all the slides in one go, and with one class I'll complete that, and then we'll move into support vector machines. Once you understand support vector machines, you are 80% good in machine learning, not the data science. Again, the machine learning, data science, AI are all inference and having used other way around in so many use cases. But as a starting point, you need to be very good at ML, and please feel free to join the rest of the journey. And I'm sure we are going to do many wonders on the way. Okay. So today we have discussed very important concepts like ridge regression, lasso, and the normalization and regularization, L1 terms, L2 terms, and healthcare terms, and how the weights can be added to the cost function and how we can minimize the cost functions. Okay, do you have any questions, Kishore? Are you happy to this point? I've prepared very less slides because I'm seriously getting not time. So I'll try to allocate some time for that. And Kishore, keep taking calls. Okay, try to do not miss any call. Call back each recruiter. Again, don't forget to update. I know we have applied only on Sunday. Yesterday is Monday. I'm not sure if you have applied. One more thing, if someone is asking you for references, you have all the authorization to tell them, I can only provide the references only after the second stage of interview. Because recruiters have this bad habit. If you give a reference, they'll call your reference and ask, boss, I want to know if I can be of any help to you in your business. I can provide clients to you. That's how they behave. So please be very careful. If anyone asks you for references, tell them as per the recent GDPR and corporate security governance, I'm not supposed to give you any references. However, if it is mandatory, I will be happy to give the references after the second round of interview or below or before the documentation work starts. I repeat, as per the recent GDPR policies and the corporate security governance, I'm not supposed to give you any references. However, if it is mandatory, I can help you on that after my interview stage and before the paperwork stage. Simple. One more thing, talk matured. At times, at times, what happens is the recruiter who is calling you might have worked with that client what you have mentioned in your CV, and he's trying to find out to what level you are aware of the team inside. At that time, tell them very clearly, boss, my client is huge. My client has got many verticals. You might have dealt with one vertical, and I might be working in other vertical. That doesn't mean that I have not worked there. That may be true. Okay, let's take a company X. Company X may have n number of divisions. Each division will be working with each recruitment agency, because each division will have a dedicated HR team, dedicated process team, and dedicated consultant team. Okay, so please be smart. You need to be aware of the whole corporate structure, how it works. Handle the calls carefully. Every call you miss is an every opportunity you miss. Take it very seriously. Again, start applying for the roles right now. Early in the morning, start it, apply, and go to your daily routines. And then by the time recruiters comes, they will find your CV on the top and they'll give you a call. One more thing, most of the times you'll get the calls from 9 a.m. to 2 p.m. max. After 2 p.m. you won't get calls. You need to be very active in this times. Every call you take is every new experience. Every new experience is like you're maturing yourself in terms of handling the calls. And keep on telling this, take it very seriously. I wanted to see a proper fallback of the calls taken and how many have been scheduled for interview. Okay, I'm pausing the recording now.
This conference will now be recorded.
Okay, I was just talking to something offline to Kishore. So that's the thing. People who are active in the market, who are started taking calls, please, it's my honest and sincere request. Every call you take is every opportunity you are enhancing, you are experiencing. If possible, try to record all the calls, because that will help you in understanding how maturely you are handling the calls in every move. Okay? Put the first phone in the loudspeaker, record it with the second phone, and do it that way. Okay? Thank you everyone. Have an enjoyable day. I will wrap up I will wrap up this concept with tomorrow's class, and next we can start support vector machines. Once we finish support vector machines, I'll let you all do the proper use cases. Then we are all done and dusted. Okay? Thank you guys. Have an enjoyable day. Take care. I'll upload the recording shortly.